So till now we have seen the different types of axial loading problems which we can come across, and now there is another concept which we haven't discussed till now, which is very important, and that concept is something like this. Suppose you have say a cuboidal rod like this, okay, and and then you applied a force like this in this direction, okay. So obviously it will get elongated in this way, but then there is a property of material, okay, which we have observed basically, is that not only this gets elongated, but also what happens is the other dimensions, the lateral dimensions, they get shrunk, okay. So for example, suppose this side is fixed to the wall or something, so then it will become a smaller version of this, and then maybe it will be like that, okay. So here something like that. So lengthwise it has increased, but width and depthwise it has reduced, okay. Now so this concept or this observed phenomena is represented by a parameter which is called the Poissons ratio, okay. So now this is denoted by the symbol nu, okay, generally, and then how is it defined? It is defined as, say, nu is defined as negative of, your lateral strain to your axial strain, okay. So that means, say, suppose I'll draw say, so this axis may be your x-axis. Now suppose this is your y-axis, and say this is your z. Now because we are applying the load in the x direction, and that we will call the axial direction, and the strain in that direction is called axial strain, okay. Now suppose that means if this increment is, say, delta, and its original length was, say, L in this direction, okay. So the strain in the axial direction, which is denoted by epsilon x, will be obviously delta over L. Now because of this, some reduction has happened here, okay. Now that is will be given by whatever length change has happened. So now suppose this I call delta x. Similarly, we will have, say, epsilon y will be delta y over this is in y direction, this I'll call, say depth d, and this is, say, width w, okay, length, depth and width. So y direction is corresponding to d, so this is your d, and because it's a compression, so it will be a negative sign should be there, okay. So delta y is a compression, and exactly in the same way that epsilon z will be negative of delta z divided by w, the width. Now what this equation tells you, or the definition of Poisson's ratio tells you, is that nu will be equal to negative of lateral, that is epsilon y over epsilon x. or the same thing can be said is epsilon z over epsilon x, because both y and z are the lateral direction displacements or the strains. Okay, and this negative sign takes care of this negative signs to give you a positive Poisson's ratio. Okay, so that's the reason why you have this negative sign over here. And then in fact it tells you that if this is an extension and this will be a contraction, so they are in the opposite sense in a way, and that opposite sense movements are compensated by this negative sign to keep nu a positive number. Now here one point comes up which is very important to notice, that it doesn't depend which direction we call as x, which we call y or z, the Poisson's ratio will be the same. At least it's assumed for the materials which we will be dealing with in this subject. Okay, and this property that any orientation you pick, okay, or for this xyz coordinate axis, these equations can be written and they will be valid. Now this property is called the isotropic property, and another property that anywhere in the material we check this thing for their values, so we will get the same values, okay, for nu, and that property is called the homogeneous property. That means from point to point, if we change in space in the material, the value of this nu or the Poisson's ratio, it doesn't change, and so that's the homogeneous property. And if we change the orientation of our axis, again still nu doesn't change, so that's the isotropic. So for us, all the materials that we will deal with in this course will be homogeneous and isotropic. So you have to think of these two properties whenever you use them. Okay, otherwise what will be a confusion is if suppose I apply force in this direction, z direction, what will be the amount of contraction that will happen in my x direction. So again, it doesn't depend on the orientation. You can think that okay, this is my actual x, so this will be my lateral direction, so again the nu will be same. So this is a much more valid way of thinking, lateral to axial. So whatever direction you are pulling or pushing, so that becomes your axial direction, and the other two perpendicular directions becomes the lateral direction for that particular axial loading. So this sentence which I now told will be very useful when we go to write the equations of the strains when loads are being applied on all the three directions, which we will be calling that as multi-axial loading. But before that, I'll just, for completeness, I can write one point here. Now if this is so, so this is nothing but in terms of sigma if I want to write. So this is sigma x over E, right? And E also is same from point to point and in all direction because of homogeneity and isotropy. And if that is so, then Ey can be, or epsilon y can be written as say negative nu sigma x over E. Similarly, epsilon z also can be written as negative nu sigma x over E. Fine, because Ey is nu times E, epsilon x, yeah. So these are the strains which we get when you apply a stress in x direction. The strain in y and z direction are given by this. Okay. So now by using these, we will now try to write the strains when the stresses are getting applied on all directions. So now consider a body like this, okay, and which is being subjected to, say, in this direction with sigma x. So this is the stress in this direction, and in this direction say sigma y, and in this direction say sigma z. Okay, so these are the stresses which are getting applied on this particular body. Now let's try to write the strains in all the three directions. Okay, so let's see. Now what will be, say, epsilon x? Epsilon x will be, first see about the contribution from sigma x. So because of sigma x, you will have the terms like sigma x over E. Okay. Now similarly, if I want to write, say, epsilon y, because of sigma y, it tries to get extended in that way. Okay, so I'll write the sigma y part like this, say sigma y over E, and similarly epsilon z is equal to, now say sigma z over E. Now I have written in this way because I'll have to fill in some other components. These are not all the full expression for the strains, so we will have some other terms, so that's why I have written like this. Now let's see. So if we see about on the x-axis, so this is the contribution from sigma x, but when sigma x is acting, at the same time sigma y also is acting, right? Now for sigma y, x direction is the lateral direction, right? So because of this pull, this x side length will be compressed a bit, and now how much will be that strain? So it should come as, you know, negative of nu sigma y over E. Now this term is like this. See here, when I'm applying, or when my axial direction is y, my lateral direction will be x, you know. Or similarly, when so in this case, that's what we have written. So I'm considering that y is my axial direction, sigma y is getting pulled, so because of which a compression is happening in the lateral direction of x. So these portions are lateral in a way. Okay, yeah. And similarly another term for this one, nu sigma z over E, because if you consider sigma z to be axial, then x again is lateral for that direction. So this is the lateral component for z direction. This is the axial component for x, lateral component for y, which is axial for x in a way. Okay, so in that way now we can fill in other things, that here you will have negative of nu sigma x over E plus here minus nu sigma z over E, and here negative nu sigma x over E minus nu sigma y over E plus this. Okay, now so these are the complete expressions considering all the extensions and the contractions when the forces or the stresses are getting applied from all the directions. Okay, sigma x, sigma y, sigma z, everything is acting. So I think it's correct, x, y, z, x, y, yeah, that's fine. Okay, now one point which, yeah, and then sometimes this is called the generalized Hooke's law. In fact, we will write once, so there is another set of three equations for the shear strain. So these are only for axial loading which we are considering, that's why we are writing only for the normal strains, okay, epsilon x, y and z's, and they are resulted from the normal stresses sigma xx, sigma y and sigma z, and the Poissons ratio. Okay, now we will come to that later, but then so here one more point which I wanted to make is, suppose you have, say, sigma x, sigma y, sigma z all are equal in a particular case. For example, suppose you have taken this block underwater. Now you know that pressure, and then assume that the depth to which you have taken is much larger than these dimensions of the block. That means the pressure is not varying across these surfaces. That's the assumption. Under that case, all this sigma x, sigma y, sigma z are negative of the pressure value, right? So in that case, these equations will be what form they will take. You can just write them. So all the sigma x, sigma z, sigma y's will be, say, negative of the pressure which is acting, and okay, then what? The E also is coming out, and here you will have 1 minus 2 nu, right? And this also, if you write here, minus P over E 1 minus 2 nu, and similarly here minus P over E 1 minus 2 nu, right? So that's the it's a very special case when all sigma x, sigma y, sigma z's are same and then negative. Okay, so just to tell you that the strain in that case is always same in all the other all the three directions. Okay, so that was about the concept of lateral strain when you apply axial loadings, and so this kind of situation is called multiaxial loading, and this is called the generalized Hooke's law, at least the Hooke's law for the normal stress and strains. So see you, we'll stop in this segment and see you in the next segment with another topic. See you.